If you were here on Friday, you know that we discussed a method of approximating the zeros of a function called Newton's method. Now, the zeros of a function, other words that you may be more familiar with than zeros, those are the same as roots of a function, or probably most familiar. These are just x-intercepts. They're called zeros of the function because it's the value of x where y equals 0. Okay, the way the process works very quickly is, if you've got some function and you're trying to find this guy here, here's our c value that they're talking about. First of all, the function has to be differentiable on an open interval containing c. Now, we know that differentiable implies continuity, so it also has to be continuous. They don't have to say that because they told you it was differentiable. Now, what the process does is that it comes up with the equation, given an initial guess that's called x1, it comes up with the equation of a tangent line. And what happens is that if the method works, that the tangent line will cross the x-axis closer to the 0 of the function, which is c in this case, than the original guess did. That's called our next guess, x sub 2. And then from that next guess, the process just repeats until we get as close to our 0 as we want. The formula there for Newton's method then is the formula that comes from getting the equation of that tangent line and then setting y equal to 0 to find the intercept. Now, Newton's method doesn't always work. One reason it might not work, if you think about the equation, in that second part you've got this f of x sub n over f prime of x sub n. So if you would ever hit a point on a curve where your guess took you to a horizontal tangent, the method would fail. Now, typically what you will do is you'll just choose another point and it will work the next time. Choose a different point that doesn't lead you to that horizontal tangent. It could also fail where, and as an example 3 in the book, where the values don't converge, and I think that was the graph of x to the 1/3 power there. Okay, but in general this method's going to work. Now, let's show an example of how it does. Here's the problem I'd like you to do. I want you to do just number 1 and come up with 2 iterations. So I'm going to do this example number 2 as our, something for you to follow. So over here I've got this example 2. F of x is x cubed minus 3, and we're coming up with the first guess, that's 1.4. And in black, that's the Newton's method formula, and I wrote down what the derivative was because we're going to need that for the denominator. Okay, so x sub 2, that's going to be our first iteration, will equal x sub 1. Well, x sub 1 is that 1.4 minus the function at 1.4. Well, that would be 1.4 cubed minus 3 divided by the derivative at 1.4, which would be 3 times 1.4 squared. Now, out of my calculator, I've already got that number, and that number is 1.4435. So we've done one iteration of Newton's method. We've gotten closer than our original guess to the 0. So what we're going to do now to generate x sub 3, which will be our second iteration, x sub 3 is I'll use that 1.4435 as my x sub n minus 1.4435 minus 3, and that should have been cubed in the original, so I'll fix that, and cubed. Oops. I was okay in the original. I just missed the cube on my second guy right there. X cubed minus 3. Divided by 3 times 1.4435 squared. And that number will be our value of our second iteration of Newton's method. Let's see what we get here. 1.4435 put in, and out of it is 1.4423. Okay, let's see how close that's coming to the real answer. So after 2 iterations here, what we're really doing, if we'd let y equals 0 in our original example up at the top here, you'd be solving 0 equals x cubed minus 3. So we're really finding the value of the cube root of 3. And off of my calculator, the cube root of 3, 3 raised to parentheses 1/3, is 1.442. 22. So we're within 1,000th of the real value right here. Okay, so that's all you need to do. Do 2 iterations of Newton's method on problem number 1 and show your work.